Assalamu alaikum students. In today's lecture, we will learn about the electronic configuration and magnetic properties of the atoms. Now, it will include definition of electronic configuration, then how to fulfill the orbitals according to their relative energies, then rules for the distribution of electrons in the different energy sublevels or the orbitals. Then the magnetic properties will be discussed, and at the end there is given a worksheet. Now students, before I start to tell you that what is meant by the electronic configuration, I hope you are familiar with the previously done definition of quantum numbers, that these are the four integers which are having the different one values and which describes you the size, shape, energy and the spin of the electrons, and it is divided into four types. Number one, n, which represents you the shell number, and it also tells you about the energy of the orbit. They are k, l, m, n once again, and the total number of electrons which can be accommodated in the shells, that will differ with the change of the number of shell. For example, the first shell can hold only 2 electrons, the second one will hold 8, right? Now the next one, second quantum number, is azimuthal quantum number, which is also called angular momentum quantum number, which is related to the angular momentum of the electron. According to this, there are four subshells which have further orientations in space represented as m. Now there are four quantum numbers that is under the heading of the azimuthal quantum number. They are namely S, P, T and F. Each one is having a specific shape and orientation in space, so it is further divided into the orbitals. S subshell is having just one orbital, that is of spherical shape. It can hold just 2 electrons in it. Now P subshell is further having 3 orientations in space in the form of orbitals. These orbitals, they accommodate in total 6 electrons, while D subshell, it is further subdivided into 5 orbitals, or you can say it has 5 further orientations in space represented by M, and each one orbital can hold only 2 electrons, so the total number of electrons present in D is 10. And then we have F orbital, which is having the value of L, that is 3, and it has 7 orbitals with it, or 7 orientations in space, and each one can hold 2 electrons, so the total number which can be accommodated in F sublevel is 14. Now the value of L for S is 0, for P it is 1, for D it is 2, and for F it is 3. This will give you that how the electrons will be accommodated in the sublevels or the orbitals, right? Now this one quantum number, again summary is given to you. This is due to that we have to arrange electrons in an atom according to the these sublevels or the orientations in space, right? Now, how will you define the electronic configuration? Electronic configuration actually is the arrangement of electrons in atoms in such a way that the various orbitals around the nucleus of atoms, they are filled, in which electrons are arranged. So this is termed as electronic configuration. Now the question is how the electronic configuration is given or it is written for a specific atom, or how to fill the energy orbitals or the shells or subshells. So there are 3 basic rules which are used for this purpose. They are namely one by one. First one is upload principle, the second one is Pauli's exclusion principle, and the third one is Hund's rule. They will give you how the electrons they are filled in different energy levels, and they will tell you about the electronic configuration of atoms. Now come to the next one. Here the relative energies of atomic orbitals are mentioned here. You can see this chart is giving you the increasing order of the energy sublevels and their orbitals. Here you can see in this diagram n number it is represented. N tells you about the number of the shell. So first shell is of the low energy, for which there is only one orbital that is present, that is s orbital, for which the value of L is 0. It is of the lowest energy and it will be filled first. You can see it in this diagram at the left hand side, right? There the orbitals are arranged according to the increasing order of their energy. So it will be filled first. That is 1s orbital. For each atom you will start to write the configuration with respect to the first one shell. The 1 along with this S represents you that the filling will be there in first shell, and S represents you the which one orbital will be filled, right? Now, and when there is N is equal to 2, it is the next higher level, that is the second level. It has two orbitals or two sublevels in it, that is 2s and 2p. You can see 2s is lower in energy as compared to 2p. 2s is having just one orbital or just one orientation in space, but 2p is having three orientations in space, namely px, py, and pz. The filling order will be after filling first orbit, you will go to the second, and here the 2s will be filled first. As it carry one orbital, so two electrons can be accommodated in this 2s. Right? Now further we will go to the 2p, which also belongs to the second shell. After filling the 6 electrons in these three orientations, once again namely px, py, and pz, then you will move further to the next higher orbit. This is the third one orbit, which has three levels in it, or three subshells in it, namely 3s, 3p, and 3d. Now here you can see the 3d level is higher in energy as compared to the 4s, as it is given. You can see, look at this one, 4s is filled first and then 3d will be filled, right? So when you are writing the notation in uh, third shell, then you will write down, after writing 1s, then 2s, 2p, then 3s. After 3p you will go further for the 4s, and then the next high level, that is 3d, will be filled, right? Now here in the fourth one shell, the filling order is also given. Here you will find 4s, 4p, 4d, and 4f. You can see in this filling order, after 4s, 3d is filled, then we have filling of 4p, and then we will move further to 5s instead of 4d, right? Then as 4d is higher in energy, so it will be accommodated with electrons after 5s filling. Then you will go to the fifth one shell, as it has been started, that 5s is filled, then 5p will be filled further, then 6s, and then you will go for the 4f, right? So you can say here the electrons are accommodated into the orbitals according to the increasing order of energy of the subshells or the orbits, right? Once again, orbit 1 carry just one subshell in it, or one orbital it carry. The second shell carry two subshells in it, or the there are present 4 orbitals, 1 belongs to 2s and the 3 belongs to 2p, and then so on. Right? So you have to learn this configuration, uh, or the order of the ascending energy of the orbitals to fill the electrons for each and every atom of the periodic table. Right? Now here the L values are also being mentioned. As I told you earlier, the L value for S is 0, L value for P is 1. For each P orbital, that is whether it is Px, Py, Pz, it is 1. For B it is 2, and for F it is 3. The most important the quantum numbers to fill the electronic configuration are N and L. Now here comes next, once again the same repetition is here, and it is also giving you how the filling will be done in different energy levels according to their ascending order of energy. Here you can see the first one shell is filled first, that is N1, it will be filled first, where there is only one orbital, that is 1s. As I told you, 1 belongs to the first one orbit. Right? Now the second one shell, that is L shell, it consists of 2s and 2p. Once again they will be filled in the order, the 2s, later on 2p, then we will go to the m orbital. The capacity total in this is 18 electrons, but the filling will go on in the 2 orbitals, that is 3s will be filled first and then 3p. But before we fill up the 3d, there will be filling of 4s, which belongs to 4th shell, as 3d is higher in energy. Along with this, there are given the electrons which can be accommodated in each orbital. Right? Now come to the next one. Now N plus L rule tells you about the ordering of the energies of the orbitals in the multi-electronic atom. The N plus L value increases with increase in the energy of the orbit. Right? Now here you can see, first of all, look at the example so that you can understand it well. You can see for 1s, if we apply the rule N plus L, you will get that which orbital will be filled first. The value of this N plus L will tell you that the lower energy orbit, or having the lower value of N plus L, will be filled first. Right? So you can see the value of N is given in 1s, it is 1, while value of L for S is 0. So the total comes out as 1 plus 0 is equal to 1. Look at the second one. 2s, 2 indicates N, S indicates that orbital is the spherical one shaped. The value of L for this S is 0. Once again, the total comes out as 2. Now you have to write that which one orbital will be filled first, whether it will be 2s or whether it will be 1s. So as the N plus L rule is telling you that 1s is having lower value of N plus L, so it is the level of the low energy, so it will be filled first. Right? Now look at the 2p. Now compare the values of N plus L for 2s and 2p. For 2p, the value is, as the N is given, that is same in both the cases, that for 2s and 2p shell number is same, that is 2, that is the N in this, and then L value for this P is 1, the total number is 3, so definitely it is higher than that of the 2s in energy, so that's why it will be filled after the filling of 2s orbital. Now look at the third one, or the fourth one actually, 3s. The 3s is holding the value of n orbital, that is 3, and then you have the value of L for this S, that is 0. The total is given 3. Now you can see 2p and 3s hold the same n plus l value. So which one will be filled first? This sub rule is indicating that you have to check now the shell number, the orbital which will hold the lower shell number, that will be filled first. So in this case, when you compare 2p and 3s, although their n plus l number is same, but the 2p will be filled first as it has the lower number of principal quantum numbers present in it, that is 2. Now come to the next one. Look at 3p and 4s. 3p, the value will come out, that is 3 is representing n, and the value of l for p is 1, so the total is 4. For 4s, once again it is also 4, as the value of n for this 4s is 4 and the value of l for s orbital is 0. So it is giving you the value that is 4. You can see 3p and 4s both hold the same value. So what you have to do? You have to fill 3p first as it has the lower number of n in it. Right? Same as for 3d and 4p. So this is the order that n plus l rule will tell you that according to the energy, which orbital will be filled first. The orbital which will carry the lower number of this n plus l, that will give you the first one, filling of electrons in it. Right? Now come to the next one. Here there are the three basic the principles or the rules which govern the arrangement of electrons in these orbitals. The first one is Apo principle, as we are discussing it from the previous one slide. That the Apo principle tells you that the electrons will be accommodated in orbitals according to the ascending order of their energy. So what will you say? In the ground state, the atoms, the orbitals which are filled in the order of increasing energy of electrons first occupy the lowest energy orbital available to them and then enter into the higher energy orbitals only when the lower energy orbitals are filled. Right? Means, look at this diagram once again. N is equal to 1. It is the lowest energy level, so it will be filled first. After accommodating 2 electrons in 1s, you will go to the 2s orbital, which is higher in energy than as compared to that of 1s, so it will be filled next. And then you can see the arrangement or the direction of these arrows, which are indicating that which one will be filled further. After 2s, it is 2p which will be filled. After completing 6 electrons in 2p orbital, then you will go onwards to 3s. From 3s, the movement will be towards 3p. After arranging 2 electrons in 3s, then 6 electrons in the 3 orbitals of p will be accommodated. Right? So as the number of n is increasing, the energy of the orbits are also increasing. So the filling of orbitals will in accordance to the energy of the levels. Right? Now here once again our principle will deal with it, according to which the lower energy orbitals will be filled first. After filling of this lower energy orbital, then there will be the higher energy orbitals which will be accommodated with the electrons. Now the next one is Pauli's fusion principle. According to this principle, no two electrons in an orbital can have the same values of 4 quantum numbers. 3 values will be same and the fourth one will be different. Now how to describe it? Look at the two diagrams. There's two. Now you can see Here in helium, one s orbital is occupying 2 electrons, while in hydrogen it is occupying only 1 electron. Both have same orbital to be filled. In hydrogen it is 1s, while in helium it is 1s. Right? Now, hydrogen, as the atomic number is there, its value is only 1. It has only 1 electron. So 1 electron will be placed like this in an orbital. As I told you earlier, the orbital can hold only 2 electrons in it, right? Keep it in your mind every time you are putting up electrons in the orbitals, right? Now here we have 1 electron for hydrogen, but for helium there are 2 electrons. Unless you are going to fill this oneness completely, then you will move onward to the second one orbit. You cannot go there before the filling of this 1s completely, right? Now this 1s is having 2 electrons in it. You can see each one with an oppositely placed arrow. This oppositely placed arrow tells you about the spin. Now you can see there is present only one shell, that is first shell in helium, and there is present only one orbital, that is 1s orbital. Only 2 electrons can be accommodated in it, and we have only 2 electrons, so they will be placed here. Their quantum number will be same, that both of them will be represented by n, that is 1. Both of them will have the value of L, that is 0. Both of them have the value of M, that will also be 0, but the spin of both will be different. One is with the clockwise spin and the other one is with the anti-clockwise spin. This is termed as a paired electrons which are placed in this orbit, right? So two electrons can reside in one orbital if they have their spin quantum numbers different, right? Otherwise they will be placed separately. Okay, now come to the next one. Here it is given once again. It is representing you the how to write the configuration, that is which one is the correct one according to the Paul's fusion principle. Here you have the 2 electrons. You can see in the picture there are given 3 pair of electrons. In the first one or the left side diagram there are given 3 pair of electrons, each with an opposite spin. This is called as the correct one value or the correct one placement. While look at the second one arrangement on the right hand side, you will find there in 2s2 there are present 2 electrons but are with the same spin, right? So this type of orbital is not valid. 2 electrons cannot be placed like this in one orbital. All the 4 quantum numbers cannot be same, right? So this is an invalid or the wrong one configuration, while first one which is given on the left hand side, that is the correct one configuration according to the formula, right? Now next one is the Hund's rule. Hund's rule says if degenerate orbitals are available, then each will be filled half first and then its pairing will be done, right? Now, how to explain it? You are familiar with that p orbital is further subdivided into px, py and pz. Only their orientations are different but their energies are same. They all belongs to one subshell, that is p. So their configuration will be written as, you can accommodate 2 electrons in px, 2 electrons in py, 2 electrons in pz. If all the 3 are available and you have 3 electrons to place in p orbital, you will not place 2 electrons in px and 1 electron in py, but instead of this, what you will do, you will place 1 electron in each of these orbitals with the same spin. Look at this. The configuration is given. Now here we have the filling order in which 1s2 is completely filled. It is having a pair of electron in it with opposite spin. 2s is also completely filled. 2s2 is represented there. 2 electrons are present in it, and it is having the opposite spin. So they are correlating to that of the what the we have done the previous one rules or principle. Now here we have three orbitals for the 2p level, 2p subshell, and we have just two electrons to accommodate. The two electrons will not be placed like this as it is presented on the right hand side of the diagram. You cannot place them in a pair form in only one orbital, but there is availability of three orbitals which are of the same energy, so they are called degenerate orbitals. So you have to place one electron in each, right? Means they will be half filled first. All of the three will be half filled first, and same is true for if you go for D, that all the five orbitals will be half filled first, and then their pairing will start, right? So according to Hund's rule, if you have degenerate orbitals in the atom, so each one will be half filled first, and then the pairing will be done. Now, by applying all the previous one rules, including a flow principle and the Hund's rules or Poisson fusion principle, here we are able to write the electronic configuration of atoms. The different notations which are used for this purpose, that is shown here. Longhand configuration can be given, or a shorthand configuration can be given. What about the longhand or the shorthand configuration? A complete configuration giving you all the orbitals starting from the first one up to the valence orbital. That will give you the longhand configuration. But if you are going to write only the valence electrons, and before this you are showing some of the inert gas configuration or the symbol of that element, that is of inert gas, then it will be termed as a shorthand configuration. You can see here the sulfur is mentioned with both types of the configuration. You can make a difference between these two. Now sulfur with atomic number 16, the complete configuration is mentioned. In first orbit there is completion of 1s2, and it is first shell. In the second shell, as it is also complete, there are 8 electrons are accommodated. Second shell is complete, but the third shell is incomplete. It is having only electrons in 3s and 3p, and 3p is still incomplete, as the total electron which can be accommodated here, they are 6, right? So this is the complete longhand configuration, telling you all the orbitals and the number of electrons present in them. But if you want to write a shorthand configuration, then consider the first completely filled orbitals as the core electrons, right? So up till this one, the it matches to the periodic table where one of the noble metal will be found. Now it is having the atomic number that is 10 up to this second shell, that 2 in the first one and 8 in the second one. The total comes out 10 electrons. So this is the atomic number of neon. So we will say when we are writing the shorthand configuration, up till neon the configuration is complete. That represents you that 10 electrons are accommodated, and then after this there is given the valence electronic configuration, that is the outermost shell is given, in which the orbitals are still left to be completely filled. Now the next one is the filling of the orbitals of oxygen, fluorine and neon. These are some of the examples. You can see here they are given the complete longhand configuration as well as a shorthand configuration. In oxygen, atomic number is 8. So where it is given? First of all, there is given fluorine with atomic number 9. The first 1s complete, 2s complete, 2p is also complete. Now here we have the now 2p is still incomplete. It have 5 electrons in it. The 1 electron is left. So it will be second shell will be considered as its the valence shell, right? But the first one will be termed as a core electrons, or it is matching to the inert gas configuration, that is helium. So when you are going to write the shorthand configuration, it can be given like this, that up to the helium configuration is complete, and later on there is 2s2 and 2p5. which is the valence shell electronic configuration, right? Now here this is the long hand, and then onward there is the short hand configuration of fluorine. Similarly, you can see with oxygen having atomic number 8, two configurations are mentioned. One with the ascending level of the orbitals which are filled. First shell is complete with the two paired electrons in it, right? Second shell may 2s is also complete as it also carry two electrons in it, but the 2p it is having vacancy of still two electrons in the orbitals, right? So the configuration which can be given as the long hand will be 1s2, 2s2, 2p4, while its short hand configuration can be given as only first shell is complete here, second shell is still in the process of completion. So up till the first level, the configuration of helium is being complete. So you will write helium before the valence shell of the oxygen. Similarly, here neon, once again, the three of its, what you say, notations are given. One with the arrangement of the orbitals in ascending order of their energy, following the Bohr principle. Secondly, it is following the Pauli's exclusion principle, where two electrons are placed with opposite spin in the orbits, and then it is having the application of the, what you say, Hund's rule as well. Now here in neon, what the configuration is given, that is 1s is complete, first shell is complete. In the second shell, there are both orbitals are also complete, that is 2s and 2p. The maximum capacity is done, right? But that will be considered as its valence shell, outermost shell. So you can write up to helium, that is this one is the core configuration of the neon, and then later on you have the last shell with the electrons present in it, right G? Now the next one here, the behavior of the different substances when they are placed in the magnetic field, whether they are paramagnetic or the diamagnetic. If the substance shows response or it is attracted towards the magnetic field, then it is termed as a paramagnetic substance, and if it is not attracted towards the magnetic field, then it is termed as diamagnetic, right? It is under the influence of magnetic field, whether they are attracted to the magnetic field or whether they are repelled by the magnetic field. So which ones are attracted, they are paramagnetic, and which ones not attracted or they are repelled, they are the diamagnetics, right? Now here each atom is holding some property. Now here some of the examples of diamagnetic and paramagnetic atoms are given. To find out that which elements or which atoms they are paramagnetic or diamagnetic, you have to place them under the magnetic field, and you should know their electronic configurations. If they are attracted in the magnetic field, you will call them as paramagnetic, and if not, then they are called as diamagnetic. Once again, paramagnetic behavior comes when atoms are having unpaired electrons in them, and if all the electrons are paired, the substance will be diamagnetic, right? Now here from the configuration you can get it easily. Here for hydrogen it has only one electron, so we will say yes, it is attracted in the magnetic field. So as it is having just one electron in it, what about helium? Helium is having two electrons in its 1s orbital, so it is a paired one electron pair, electronic configuration in it, so it will not be attracted in the magnetic field. You will call it as the diamagnetic substance. What about lithium? What about neon? So you have to find it out yourself. Once again, it's up to you that how will you get that which ones are the electromagnetic, paramagnetic, and which ones are the diamagnetic. Write down their configuration, you will get it. Some of them are mentioned at the end, right? For example, in beryllium, there are mentioned 1s2, 2s2, two orbitals are completely filled, so it will be diamagnetic in nature. But in carbon, you can see here the configuration is 1s2, 2s2, and 2p2. So as p orbital is empty. It has two half-filled orbitals in it. So here will be the paramagnetic behavior given by this carbon. While oxygen, it is having, what is the configuration of oxygen? As it is mentioned here, 1s2, 2s2, 2p4. One orbital is completely filled and the other two are half filled, as it can be given previously. It is given on the slide, so you can get it from there. Right? Now here once again some of the elements along with their shorthand configuration are mentioned, telling you about the valence shell electrons, whether they are behaving as paramagnetic or diamagnetic. You can get it easily. Right? You can see here neon itself, it is diamagnetic. All the noble gases, they are diamagnetic as they have filled one electrons or the orbitals in there. Right? Now here next onward there is given a worksheet. This